Okay, so hopefully we'll finish off here. Okay, so the other one is when A and B are independent. Now, what this means, it's kind of different. It's kind of weird to describe this. I would say that, yeah, it's written there. They're independent if one happening doesn't change the probability of the other happening. So we'll see examples below, and we also see the. We should write down the general formula as well, which says that the probability of A and B is equal to the probability of A happening and the probability of B happening given that A has already happened. Okay, this is called a conditional probability. And I think we'll look at an example on the next page, and we'll look at okay, so what that actually means is that if A and B are independent, this should just be equal to the probability of B. So A, B, independent, basically kind of just means they have nothing to do with each other. A, B, independent if the probability of B, given that A is true, is equal to the probability of B. And it'll also be the same as the probability of B given that A is false. So that'd be the probability of not A. Or sorry, the probability of B given not A. It'd be the same thing. So it doesn't matter if A happened or not. Okay. So an example, draw a card X1 from the deck and replace it at random. Now draw another card from the deck X2. What is the probability of two aces? And we're going to look at the probability of getting, if we don't replace. Okay, so if you replace, say there's, okay, so think about the two events now. So the events are, you have a deck of cards, you pull out an ace, you put it in at random, and you get out an ace again. Now, on the second time you take the ace, it doesn't matter if you got an ace the first time or not, because you put the card back in at random. So these events are independent. So I'm just gonna claim that. So the two events x1 equal to A and x2 equal to A are independent. And that means that the probability of getting the first card equal to an ace and the second card equal to an ace, x1 is the random variable, the first card, x2 is random variable, the second card, should be the multiply the probabilities together. x1 is equal to A times probability that x2 is equal to A. Okay, so I think in terms of the assessment, I'm probably going to assess more, are these events independent? Are these events mutually exclusive? Rather than necessarily calculating probabilities. Okay, so what's the probability that the first card is an ace? Well, there's 4 aces out of 52, and if you put in whatever card you get, in particular an ace, at random, there'll now be 4 aces out of 52, and I think that's equal to 1 over 169. I think. Yeah. However, if we select without replacement, so that means to get the first card being an ace and the second card being an ace, if you don't put the first ace back, certainly at random, there's only 3 aces in the deck, so it should be given like this. So in this case, I'm just going to continue it from here. What's the probability that the first card is an ace? 4 out of 52. And what's the probability that the second card is an ace given that the first card is an ace? If the first card is an ace, there was 52 cards, you took out 1 ace, and there's only 51 cards, and there's only 3 aces. So the probability of the second card being an ace is 3 out of 51. And whatever this is equal to, 4 by 3 over 52 by 51, 1 over 221. It's smaller. You're less likely to get 2 aces if you don't put the card back. So, example of non-independent events would be the event of Dublin winning the All-Ireland and Kilkenny winning the man of the match in the final. So if you're into betting and you want to put on a double, usually you'll be putting on a double two events that are independent, say Manchester United winning a match and a horse winning a race. One of them happening has no effect on the other, so what they do is just essentially multiply the probabilities of the odds. But if the events are independent, the I can't remember the language that the bookies use, related events or something like that. So related would be non-independent. So they won't give you multiply the probabilities. They will instead they'll come up with a different figure. So for example here, if they were looking at this event, they'd look at Dublin winning the All-Ireland and Kilkenny winning man of the match. They'll give you the probability of Dublin winning the All-Ireland. That'll be the normal odds. And then they'll look at the probability of the odds of Kilkenny winning the man of the match, given that Dublin won, which will be a much higher probability than just not including that. So if Dublin win, it's more likely the probability changes, so they're not independent. I think that's all I wanted to say there. Yeah, so the other thing is you could actually do probability of Dublin winning, say Dublin winning and Mayo losing. But obviously they're related, they're actually the same. Usually if it's Dublin Mayo final, that's the same event. So you can't get a double like that. Okay. So let's see. A deck of 52 cards contains 13 cards of spade, heart, diamond, club. What is the probability that 2 cards dealt randomly from the deck will both be spades? So first of all, it's not true that spade and spade, you multiply them, as picking a spade the second time is less likely when it's already been taken out of the deck. So what we're looking at is the probability of spade and spade is equal to the probability, and I'm going to write x1 for the first card, that the first card is a spade times the probability that the second card is a spade. Now, this equals isn't great. I'm going to write just my own squiggle there. Given that the first card is a spade. So what's the probability that the first card is a spade? And it doesn't say, now the 2 cards are, so there's no replacement here. So what's the probability of a spade? Well, there's 13 spades out of 52, or you can say 1/4. And then what's the probability of getting a second spade, given that the first card was a spade? Well, now there's only 12 spades in the deck, and there's only 51 cards. And we can calculate this number here. 13 by 12 divided by 52 by 51, which is 1/17. Okay, so what I'm doing here in this section, this is actually like a further comment. So really what is important here? I think each of the 4 remarks, some of which are in the previous lecture, are the important things. So things that don't happen with probability of 0, or things that always happen, probability of 1. If things are mutually exclusive, the probability of A or B, you add the probabilities. And mutually exclusive means that they can't happen at the same time. Probability of not A is 1 minus probability of A. If events are independent, which means one of them happening does not affect the probability of the other one, the probability of both happening, you multiply the probabilities. If they are what the bookies would call related, or what we call not independent, you have to use conditional probability. And we did some examples of that. Now what I'm probably going to do in the assessment, as we'll see in the next page, the questions are going to be about events. Are they independent? That might be something I ask. I probably won't ask you to calculate probabilities. I can almost certainly tell you that because I have no exercises for it. Okay, now I'm just going to kind of expand on this idea that the probability is a function from the events to 0, 1. This is just kind of pushing this a little bit further. You don't necessarily have to know this, but it can help your understanding. So this is actually a further remark, which means that it's just something that if you want to deepen your understanding, you can read. I'll actually go through it. You can skip it if you want. I think you're better off though. So the usual way mathematicians think about probability is something like the following. First of all, we've said of outcomes. So for dice, the outcomes are 1 to 6. Then we've said of events. So they're thinking of combinations of outcomes. So the events here are usually, now I usually put them a little differently. So the nothing happens, you write as curly brackets with nothing in it. This, you usually put curly brackets around it. Tail, curly brackets around it. And head or tail, be curly brackets with head union tail. So we have a probability which goes from the set of outcomes to numbers between 0 and 1, which assigns to each event a probability between 0 and 1. Actually, after this, I must remember to go back. Just a note for myself. So, for example, for a single coin toss, probability of a head is 1/2. So the input is, say, head, the output is 1/2. We can consider random variables. So random variables go from the set of outcomes to what's called a measurable space. Now, we won't worry too much about what measurable space is here, because myself, I can't really think about what it is. So, for example, the set 36, 1 to 36 is a measurable space. And where the set of outcomes, so here you've got all the possible outcomes when you roll 2 dice. And suppose that the random variable, so the omega here would be, say, D1, D2, outcome on the first dice, outcome on the second dice, and the outcome is you do D1 multiplied by D2. This is a random variable. So let's think you roll 2 dice and you multiply them together. That's a random variable. The probability that the random variable is in some set is, so this is a kind of a complicated business. It's kind of saying that if you want to, so the random variable goes into a measurable space. That's where you can kind of assign probabilities. And so this is basically saying that the probability that X ends up being somewhere is equal to the probability of, it looks at all the possible outcomes that put you in that set, something like that. So for example, where you've got a random variable which takes in essentially 2 dice as the input, the output is number between 1 and 36 is the product. So for example, if you roll a 3 and a 4, the output is 12. The probability to get 30, you look at all the possible outcomes that make the random variable equal 30. This is probably confusing, I'm sorry. Is 5 and 6 or 6 and 5. And that's 2 of the possible outcomes out of 36. Okay, now I've made a little note for myself just to go back to head, head, head. And that is back on page 124. So back here. So this was really about if you want to calculate something that's kind of complicated, it might be easier to calculate what's called its complement than not of it. And here we're looking at head, head, head. And it's when you roll 3 or flip 3 coins, and here we actually listed all the outcomes, but actually because like when you flip coins, the outcome of one does not affect the other. So they're independent. And if they're independent, I can multiply the probabilities. So the probability of head, 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 because they're independent, it'll be like that's head and head and head is probability of head multiplied by probability of head multiplied by probability of head. And each of those is a half. So it's a half by a half by a half, which is an easier way probably of getting this 1/8 figure. Right, so let's look at what might look like an example of a question. Now, obviously, later in the chapter we've got calculations, but at the moment we're just interested in those 4 remarks. So let's see some questions. So these are actually questions on exam papers last year, but of course you've no exam papers, so let's see. So consider 2 factories called A and B, run by 2 different companies using different raw materials, different production methods in different parts of the world. Okay, so basically the 2 factories have nothing to do with each other. Okay, so consider the following random variables. The lengths L1 and L2 of 2 randomly selected rods from the same batch produced by factory A. So length of 1 rod, length of a second rod, both chosen at random. And length 3, the length of a randomly selected rod from factory B. So you got these 3 rods, 2 of them from the same batch in one factory and 1 from another factory. So consider these 3 events. The first event is that L1 is less than 8 meters. Now I'm going to think of this as being short. So this being short is the first event. This being short is the second event. And this being short is the third event. Okay. So the first question here is, are events E1 and E2 independent? Now, this is a tricky enough question, but so these are made in the same batch. You see the thing, yeah, so you might say, well, one has got nothing to do with the other, but And in fact, probably if you argue it, I'm probably going to have to give you the marks, like it's not 100% on this. But the way I'm probably thinking about it, probably the question isn't ideal. It's probably to say, so don't say at this point they're from the same batch. So L1 is randomly selected rod from factory A, and so is rod 2. And the question is, are the events that these rods are short, are they independent if from same batch? And the answer would be no then. You could kind of argue yes and just say they're nothing, but because they're in the same batch, if you got one wrong or one short, there's a higher probability that it's actually a bad batch. And so if one is short, it makes it slightly more likely that the other is short. So let's write that down. So, are not in the back-ended because L1, now we can say L1 being short or L1 being less than 8, or we say E1 being true. So let's use the language of true. E1 true. So being true is just another way for saying that the event happened, or let's say happened. Because if event 1 happens, and this is all kind of possible. I appreciate it's a difficult theory question, but these are very important things. Understanding these. Possible that it is a bad batch. Making E2 more likely. And that's what not independent is. When one of them happening changes the probability of the other. Possible that it is a bad batch. Possible that it is a bad batch. Making E2 more likely. I'm trying to think of something that you kind of buy in a shop and you get a bad, like I think a good example of this could be mandarins actually. So I don't know if you eat mandarins, but you can get kind of duds. They taste crap, or they kind of get this nasty core. So if you talk about two mandarins at random, they're probably independent. But if they're both in the same net, if you get one bad one, it makes it more likely that the next one is bad. Something like that. Or even, yeah, that's probably another thing, is things going off. So I can't think off the top of my head, but maybe like if you have a bowl of fruit, and if you get one apple going bad, it makes it more likely that another one goes bad. So the probability that the two apples, or not even the probability, the events that the apples are bad is not independent. Something like this. Okay, now E1 and E3 is way easier because E1 is in factory A or it concerns factory A, and E3 concerns factory B, and these two things have nothing in common. Like they're all using different, everything is different. E1 and E3 are independent because E1 happening does not affect the probability of E3. It's probably the best way to answer. Okay, so a hard question and a kind of easier question. So next one. So who knows what I'll put on your assignment. So consider the random variable length of a randomly selected rod produced by a factory. Consider, so you just have one rod now that's selected at random. Consider the events E1, E2, E3 that the rod is short, not equal to 8, and long. So the first question is, are events E1 and E2 mutually exclusive? So can a rod be short and not equal to 8 meters? Yeah, it can. So they can happen at the same time. So L less than, oh that's right, E1 and E2. E1 and E2 can happen at the same time. For example, if the length was equal to 7 meters, it would be less than 8 and it would be not equal to 8. So E1 and E3 are mutually exclusive because not possible that the length of the rod is less than 8, short, and long at the same time. So some difficult theory stuff here, no doubt. We'll see what I have in store for you in the assignment.